All right, everyone. Thank you very much for attending today's Sumo Speaker Series event. Today we have the very good fortune of having Stanford's Poincaré visiting professor, Mark Levi, give a talk on physics in service of mathematics. Professor Levy's journey with math and research actually began in physics, but after emigrating to the United States, in the wake of the collapse of the former Soviet Union, Professor Levi found himself surrounded with these sort of legendary mathematicians, and ended up doing a PhD in mathematics under Jürgen Moser, which some of you may be familiar with if you're at all had experience with partial differential equations. Today's talk is a bit non-standard in the sense that it is not one topic, but rather a series of vignettes of various different ways that one might apply physics to mathematics as opposed to the standard way that it is usually done the other way around. So without further ado, I'd like to hand over to Professor Levi to begin.
Thank you very much. It's a pleasure to be here, and I'm very happy to share some of the things that I enjoyed as a hobby ever since I first saw this thing that just absolutely amazed me. It was totally out of the world that I studied. The fact that the Pythagorean theorem is a manifestation, it's one of the very, very special cases of the conservation of the fact that there's no potential motion machine. This universal fact, as it turns out, many consequences, and the Pythagorean theorem is one of them, which I was never told, and I saw it in a beautiful little book a long time ago. So maybe I'll ask you to vote on which problems to talk about from this list. But before, maybe I'll describe this thing that started me on this hobby. Okay? So you take the triangle, the right triangle, and by the way, this idea works for the theorem of cosines just as well. I just want to take the simplest possible situation. Now, let's do a thought experiment. Imagine that this triangle is the bottom of a fish tank. Okay, gravity is pointing into the blackboard. The fish tank is a prism shape. We pour water into it, and the water begins to push on the faces with the forces which are proportional to the length of each face, right? I can adjust the depth so that the force in, let's say, kilos or whatever newtons is shown. And I allow this fish tank, it's a crazy thing, but the thought experiment costs nothing. So I can allow the fish tank to pivot on this vertical axis, right? So this axis is vertical, right? Will it pivot? Of course not, because otherwise we have a perpetual motion machine. I mean, there is a competition between this tries to rotate counterclockwise and these two guys the opposite way, right? So it's not going to be rotating. So something is zero. What is that something? It's the torque. I don't know if I should describe what torque is to math majors. The torque, well, I'll just say it's the intensity of rotation. I apologize if I'm insulting your knowledge, but it doesn't cost much time. So I'll just say we have a wrench, and the intensity at which you turn the nut is proportional to the length of the wrench and to the force in the direction of perpendicular to the hand of the wrench. For example, if the force is applied not here, but say at another point, then I have to extend the line of force and measure the distance from the axle to the line. So the torque, each of these three forces, these torques add up to zero. Let's compute those torques. What's the torque of this? This force is A, and I must multiply it by the lever, which is A over 2. You see what's happening, right? Plus, and I count clockwise with the plus sign. Well, according to this rhetoric, I have to extend the line of force. Because this is the right angle, this distance is still B over 2. So it's the force B times B over 2, and the opposite force is C over 2. So that's the Pythagorean theorem. Okay? So you say you start with something obvious to a child. The thing is not going to rotate. All that's left is to translate into a formula, you get a Pythagorean theorem. And you don't have to invent anything anymore. If you took a triangle that's not right and go through the motions, you'll get the theorem of cosines. One time, but you could say, well, this is not rigorous. Yes, it's true, but it can give an idea of a rigorous proof. And one time my daughter came from school and asked me, why is Pythagorean theorem true? And you go through the number general, but you don't really see why. Can you explain it in one word? And this gave me the simple idea, which I'm sure is not original, but I haven't seen it. So if you think about how to make this proof rigorous, this doesn't look right. In no sense of the Okay, so you take the triangle, and the completely trivial fact that the area of the triangle doesn't change when you rotate the triangle. That's Pythagorean theorem. If you just translate that fact, the area is invariant under rotation around this vertex. You can see why, kind of, right? If you rotate the triangle a tiny bit, then the area lost through this leg is proportional to the length of the leg and to the distance traveled by the centroid, which is basically the area lost is proportional to a squared. This is sine a. And this is b squared and this is c squared, and the lost areas are equal to the gained area because the total doesn't change. So that's, I'm not going into any details. You're not supposed to understand every detail of this, but basically you just take the derivative of the area with respect to the angle of rotation, you get Pythagorean theorem. You can also discover a new completely elementary fact. What if you rotate along this vertex? Then you discover an identity for free that I have never seen. Obviously, it's not hard to prove by alternative means, but I don't see how else to discover that identity, which I'm not going to write. I can leave it as a fun exercise. See what identity about right triangles you can get by saying the area or the torque around this point. If I place the pivot not here, but here. Okay, so that's the introduction. I can now collect votes, what you would like me to talk about from this list. So how many people would like one? If this is calculus, I will select a couple of calculus problems which you can do without knowing what the derivative is. Nobody wants that, okay. We'll have another chance. I'll discuss one problem and then, well, that's good. Number 2, as you basically said. Number 3, number 4. Okay, 4. Let's see, so maybe 3, 4 votes. Number 5. 3 votes. Number 6. Okay, majority is number 6, so number 6 probably. Okay, so that's like 8 people. Okay, how about number 7? Let's do the number 7. Also second, so I would say 6 people. How about number 8? 6. These are approximate integers. So number 10 or number 9. Number 9. 2. I think there was another beginning here one day. Number 10. 2. And 11. Okay, 11 is going to be a little disappointing. Sounds more interesting. And number 12. Okay, so I think these two were the winners. So I'll start with number 6, which is Cauchy force inequality. I must say I was inspired by this by Federacion Prieto, who there's another beautiful proof which preceded mine of the Cauchy-Schwarz inequality, and it struck me so much that anyway, so the proof was essentially when you have things moving and these clump together and start moving with some velocity negotiated by the conservation of linear momentum, that's energy becomes less, so that's Cauchy-Schwarz inequality. But one time I was biking uphill and it was a very painful thing, and I saw that there was a stream by the side going in the opposite direction. I tried to take my mind off of staying, and I thought we were communicating vessels. And when you, so I'll just describe this. So if you take a bunch of, let's say, cylinders, which have all kinds of cross sections, let me just draw three, would be any number, okay? And fill them with water to different levels. So we have two vectors. We have a vector of cross-sectional areas, right? And we have a vector of heights. So two vectors, three-dimensional vectors. Right? And then we connect these by tubes and put little valves in there, which right now are still closed. And so I can look at the potential energy of this water before I open. And then I open the valves and the water comes to common level, right? And what happens to the potential energy? It becomes less, right? So, well, it would be equal only if they start out the same. So generally, it becomes strictly less after. So I'm not talking about the water doing this, it's just comes down. Okay, and this is Cauchy-Schwarz inequality if you decipher it. I can decipher it, I can begin to decipher it without, or you can go to some other problem, because I was told I should talk for half an hour, and we're half done, so.
You can take 15 minutes. You can take the full
No, I don't want, I'd rather people ask me more. So I don't want to listen too much. I'm thinking whether I should spend time on, let me just start, okay? So let's say the heights are H1, H2, H3, and the areas are A1, A2, A3, right? So we just need to write what's the potential energy before this guy. Its center of mass is at the height half h. So the potential energy is mgh. So mass of the, forget g, let's use units and we should use 1. So mass of this water is density is 1. Also, so mass is probability, right? And the mass is what? It's the area times the height, AH, right? That's mass. G is 1, and the height is h over 2. So that's AH squared over 2. That's potential energy of each of these guys with subscripts 1, 2, and 3. Okay, so in other words, the left-hand side, I apologize, I should have erased it. So the left-hand side is the sum, 1/2, area h squared. So it's a k h, so k goes from 1 to 3 or to, if you want, n to n. And that's greater than or equal to the, after, what's the difference with after? The only difference is in the heights. So instead of hk, I have to put in the common height, which I call h bar squared, right? Okay, and the only other thing is we need to know what that average height is. Well, the height is the average height, but with weights. It's a weighted average, and the weights are obviously the areas of the base, right? So what's the average weighted height is we have to add the heights, each of them has to be multiplied by the proportion its volume occupied. So its proportion is going to be the total. So what's the proportion of this guy? It's the total volume. So it's the total volume divided by the total area, right? In other words, I can lump them, as a thought, I can put all these into one big cylinder whose base is this area, right? And then that cylinder contains the total volume of this stuff. So this plus this plus this is the sum of all volumes, which is the sum of AK, H, K. That's H. So let me spare the algebra. You plug this in, and you get an inequality. And then you rename things, and you get Cauchy-Schwarz inequality, which says that the sum of xk, yk is less than. Maybe I should write. It comes from the left thing. It's the sum of xk squared greater than. You see, that square is going to come from this. It's unilluminating algebra. I mean, the thinking stops after you wrote this. The rest is just routine calculations. So it's nice when you can give a punchline in the beginning of the joke, right? It's not as funny, but you don't have to wait. Okay, so I think the next winner was 11, which is finding the hope. As I said, it's a little bit disappointing, I'm afraid, of how, since you voted for it, though. So, firstly, let's look at the cylinder. Of area base is 1, and if I submerge it in the water to depth x, then the buoyancy force is going to be x, right? Buoyancy equals to the displaced volume. Density is 1, I think. How about if I was, so in other words, the monomial x I can realize by cylinder dipped into the water. How about if I dip a triangle? If I take a triangle whose height, if the height is a, the base is a. So I take a triangle like that. And if I submerge it to depth x, well, actually, let me take 2a. So in other words, what I do is I take the function, if I look at this, I take the function y equals to x. Right? This is y equals to x, this is y equals to minus x, right? If you don't like that, it's just basically, if this is a, then this must be 2a, okay? And if I dip this triangle is, think of it as a styrofoam, right? A sheet of styrofoam out of which I cut this triangle, so this has certain depth. And so what's the area here? It's, if this is x, this is 2x. So the area is base times height over 2, right? Because the triangle, so it's x squared. So in other words, I take a triangle and when I submerge it to depth x, the buoyancy force is going to be x squared. So this way I can build any monomial, x to the power n. How do I realize that? I take the graph of, well, this is of the function x n minus 1 times n. Right? The integral of that is going to be, that distance should be, so I take 2 parabolas of nth degree. And so this is how I can realize any monomial. Let's solve now coordinate equation experiment. Let's take ax to the fourth. Let me just take, I don't want to deal with negative numbers, so I put minuses. So all of the letters are denoted in positive. This is not the base of the natural lines. Okay, so how do we solve this experimentally? We take a rod, mark one point as the origin, and here's water. And now I take x to the 4 monomial, so x to the 4 would be 3x squared. So the width of this thing should, at height x, this distance should be this, okay? See what I mean? If this is x, then this distance should be 3x squared. And so even if you don't know calculus, I just need to make a shape so that when I get it to depth x, its volume displaced will be x. Okay? Doesn't matter how the details. And so what I do is, I want to interpret this quantity as a torque. So I take distance a on this axis, right? And rod, I have a rod to which I weld this monomial, part of which will be dipped. Then minus b. Because of the minus, I mark b on the opposite side and suspend at the same height the cubic guide. So I could mark this as x cubed. If this depth is x is the depth to which I submerge, right? So this buoyancy force is x cubed. This buoyancy force is x to the 4th, and so on. So let's say c, if this is c, I make sure that, sorry, these tips are the same. Okay, and finally, not finally, d is minus, so it's a minus d here. It's x, so that's actually going to be a simple triangle. And finally, E. I want torque to be positive, so I hang a little weight. Anyway, so I grab this crazy thing and I now start submerging it. And when I feel zero torque, that depth is the solution of this. Okay. Well, it does. I don't know how to find complex roots. That's a good question. In this case, they're imaginary in the literal sense. Negative. Okay, I don't care. I mean, this is just an amusing thing that I don't want to take too seriously. Okay? Although it would be interesting to see how you can actually imagine complex roots. What would it be? I don't know. Okay, so what was I erased? I should have looked at the board, but I think the Bernoulli was the next choice. Okay, should we vote again, or should I just? I'll do Bernoulli. Right? I think there were a lot of people who wanted Bernoulli's just to come. So. Overestimated Rich. Oh yeah, bounce back. Okay, the brick is the crown. We're soon out of time, so I think that's probably the last thing I have time. I will be happy to stay and talk individually, but okay. So who knows what the brachistochrone is? Okay, about half of the audience. Okay, so this was absolutely beautiful problem, you're given 2 points in the plane, and the question is to find the trough, along which a bead will slide with no friction released from rest in the least possible time. So a straight line is not a good solution because it pays to speed up as soon as possible. So probably actually initially vertical direction is a good idea, something like this. And in this case, actually, the best solution is going to look something like this. Actually, the pace to B is far to the right and not below. If B is here, if this is a starting point and the standing point, then it's going to look like this. These are kind of two extreme cases, okay? And so, how did Bernoulli solve this problem? You see, the problem is to find a curve which gives the least time. So it's kind of the first infinite dimensional calculus question. The problem is, well, not the first, Tito's problem is the first 2,000 years before. But anyway, but this is the first in the modern times. And so, at that time, we already knew that light takes time. It was a medium of, instead of physical space, it was inhomogeneous optical medium where the speed of light varies from place to place, like in a lens, right? But with gradual variation of speed of light. Then the light knows how to go from A to B. It follows Snell's law. In other words, the light between two media, like air and water, it takes the path of least time. And how does it know to do it? Well, now we know better, but anyway, the formula is the Snell's law. It's basically the relationship between the angle and the speed of light. So sine alpha, because this letter is A, and this is beta because the letter is B, sine alpha to the speed in the region A. This is, you can think of a beach, let's say beach and water. Okay. Lifeguard wants to save the drowning victim. They want to run as fast as they get there as fast as possible, and the recipe for doing so is to choose the entry into the water point so that these angles satisfy Snell's law. And that's what Bernoulli knew, so he used this law to realize the local rule, so to speak, the relationship between the curvature and the slope. So, and then it becomes a calculus problem which you solve. But let me show a simpler way which requires no knowledge of optics at all. The only tool you need is the thought experiment tool, which is a constant tension spring. So you have to be able to imagine a spring which you can stretch, but the force stays the same. Well, how would you implement such a thing? For example, you can just take a tube with a piston, and here's a vacuum, and the piston with the rod, and you can grab it like this, by these 2 points, and pull it, and the force doesn't vary. It's a constant tension spring, it's a thought experiment. So here's how you can solve this problem. To do the hard part of the problem. I don't have the time to do the whole thing, but so let's see. Here's the starting point. This is the ending point. That's what I want to build a trough. So let's discretize the problem. Before I do that, I have to say I assume everybody can calculus, right? So what do we need to minimize? I need to write just one formula, right? So what do we need? We need the time from A to B. Well, of course, it depends on the curve. So it's the integral, you add up, you divide the curve into little pieces, and how long does it take to travel each piece whose length I call ds? It's the distance, ds, divided by the speed at which you travel. And the only thing we need to know is what is the speed. Well, the speed depends how far you descend, right? So the speed is governed by the conservation of energy. Kinetic energy plus potential energy is, I choose this as zero height. And I said we release the thing at rest, so V is zero here and H is zero here, right? So that must be zero. It remains zero throughout the travel because there is no friction. And I make G equal to 1. And instead of height, which we measure up, let's introduce the y coordinate, which is minus h. So that means, and in fact, let me make G, so G equal to 1/2. I can choose units in which is 1/2. Don't want to deal with constants, which are irrelevant. So from here we get V equal to the square root of, kind of makes sense, right? The deeper you are, the faster you move. Okay? So that's what we have. The time is the sum of these over the curve AB. And the question is to find the curve which makes this kind of quote-unquote length. It's like length, but not quite, right? This weighted length minimal possible. And so the idea is to endow this quantity, which right now only has the meaning of time. Let's endow it with a palpable physical interpretation. There's a potential energy of some collection of springs. So to do that, let's divide this space into horizontal strips of equal height and replace the unknown curve. Right now it's just an arbitrary curve by broken line. And in fact, now I'll make it physical. Imagine that each straight line has a little ring that can slide with no friction, right? So all of these are rings. And I connect the rings by springs, constant tension springs. And let's call this height y sub k. So this is for 1 to k. Enumerate these. In the kth strip, I make the string of the constant tension, which I can choose. I don't have to make these strings all the same. If they're all the same, well, let me choose this. Let me actually solve a more general problem, which actually is easier. I don't care right now that it's 1 over the square root. It's just could be anything depending on y. It's some function of y. All right? Now, this happens to be 1 over the square root, but we'll find it. So let me make this constant tension equal to f of k. So let me ask, what is the potential energy of the spring, and I need the name for the length of the spring. If that was called ds, I probably should call it delta s sub k, right? So here's my question. You take a spring whose tension is always f, constant, a number, fixed constant, and you stretch it. How much work, potential energy is how much work you have to spend it to stretch it from the zero length at which I bought it from the store to the length s. That's the force times distance. Force is constant, so it's the product of force and the distance. So the potential energy of this spring equals to f of yk delta s k, right? Force times the length. And so the potential energy of the whole assembly, of this mechanical system is the sum of f of yk times the length of each spring delta sk. So you see it's a discretized integral. So, and now how would I find the minimum of this sum? I simply release the rings and let them do what they want. They'll slide, adjust, in such a way that this potential energy becomes the least possible. When that happens, each ring is going to be in equilibrium, which means that the force pulling this ring this way and this way, these forces are balancing on the direction the ring can move. Left, right. So let's call these angles, let's call this status of K, and this status of K plus 1. And the force in the horizontal direction is the F sub K. I call this sub K. Multiplied by sine of theta K. And that's the same as the force here, so it's got to be the same as F K plus 1. Sine of theta K plus 1, and that's, in other words, we see that this quantity is just constant. It's kind of understandable because there is no force acting this way. So in other words, we conclude for the general problem that f of y sine of theta equals a constant. That's the key clue. That's basically 90% of the problem. That solves the difficult part. How to find the curve? What's the characteristic property of the best curve? This is it. So in other words, for the best curve, if you take the angle between the tangent and the vertical, this is theta, then f times this angle is governed by the height. That's what it is. If you know how high, you know how steep. And that's already a calculus problem. You can, by elementary exercise, convert it into the problem y prime equals, it will turn out to be square root of y divided by, yeah, that's right, square root of y, some constant minus y. Anyway, then you can solve the separation of variables, but that's the routine part. The interesting part is this. Sorry, that's if f is what is in our case, right? F is 1 is equal to 1. If, then this equation can become, you see, because sine of theta involves the slope, right? And so you can find the derivative of y with respect to x. Anyway, and so I don't have the time for it, but I'll just say that it's a 5 minutes or less exercise to show that this curve without any calculus is a side point. So in other words, if you take a circle, a wheel, and you roll it on the ceiling like this, right? So, and see the trajectory of some particle on the wheel. That path satisfies this equation. Well, the equation f was 1 over square root of y, so it's sine for the side for the Register-Cron, this is what we have, right? That's a constant. And if you call this constant 1 over d to some foresight, then you will discover that a cycloid, which is generated by the circle of diameter d, take the circle and roll it, the resulting curve will satisfy this equation. It's a very quick exercise. Let me just say one cute thing that you observe from this exercise. If you look at the rolling wheel of the bike passing, right? And I could ask, what can you say about the direction of motion of a pebble that's stuck to the rib, to the wheel? It turns out that, so maybe I should draw it in the normal orientation. Drawn into a rolling wheel and some particle on the rim of the wheel. The velocity of this, turns out, is always aimed at the topmost point of the wheel, and that's true for every single point. All of these points, their velocities. That's a parenthetic remark. We do this. And it's, in calculus books, sometimes they prove by formulas, which is a crime, but you can do it without any formulas. Stuff. Anyway, if if anybody, you're welcome to stop by and ask me about any of these problems. My office is on the fourth floor, so I'm always available.
Professor, we actually have the room booked until 5, so if you're okay with it and if people want to like vote on more examples, then like we completely have the ability to do so.
Well, I am happy to do it, but I haven't been in the audience myself. And when people start asking questions, I pray with no more questions. So I don't want you guys to be in the same shoes. So
I mean, yeah, okay, so we could put it to like a vote of like what people would prefer. Like, would we prefer to like go through like a couple more examples since we have the time, or okay, so like hands up if you want like to go through like a couple more examples from this list. Like,
Discovering new field.
oh,
okay, so yeah, I mean, we might as well do it. We have time.
okay. Well, once I discovered the theorem, which was not new, but it was new to me. I was actually teaching a calculus class, and we had this problem, which students hated for assigning. But the question was this: you have an ellipsoid in 3 dimensions. So this is. And the question was, which tangent plane to this ellipsoid? So take a tangent plane, right? And you see, it's tangent of this plane. The ellipsoid is behind the plane. And the question is, what tangent plane cuts the pyramid of least volume? So you can match this plane, roll it on the cylinder. If you make it too vertical, of course, the pyramid is going to be very tall and volume is big, which you don't want. You want some compromise. And it takes either a messy calculation or vector calculus to solve this problem. But you can solve it with no calculus, with just high school geometry. Depends on what you need to solve. But here's, so anyway, so I remember, okay, so here's a solution without calculus. So imagine, again, it's a thought experiment that might seem outrageous, but it gives the correct answer. So imagine that this ellipsoid is a rock, and this plane is the actual physical plane, which you can push into the rock, but it cannot penetrate. Stone, right? Oh, and this is the biggest stretch. You have to imagine that each coordinate plane can be penetrated by this tangent plane. They cross each other with no effort, but there is vacuum behind this plane, and that vacuum is maintained by the coordinate planes as well. Right? So there's vacuum inside this pyramid. But there is air.
But outside it is.
So,
Outside it is.
that's right, there is still air outside. So the air presses on this pyramid, on this face, and mashes it, and presumably it will minimize the volume. Well, it's actually the case, because if you look at it, what's the volume? Volume has a physical meaning as well. It's the potential energy. Because to create each cubic inch, you have to spend 1 joule of energy. Doesn't matter what the shape is, as long as the volume. Okay, so minimal volume, which is what we want, is the same as minimal potential energy. And that's equivalent to equilibrium. When something is, when the mechanical system is the least energy position, it's in equilibrium. Well, that's it. So this triangle is in equilibrium under the influence of uniformly distributed pressure on one side of it and the point pressure on the other. But we know this kind of thing, right? That's called the centroid. You have a lamina, a triangular lamina, which you hold with a needle below, and the gravity instead of the air pressure is uniformly distributed over the gamma. And this is an equilibrium. That point where it's an equilibrium it's called the centroid, so the central mass of the triangle. So that's the solution. Okay, you arrive at it by one calculation using calculus, and you still don't see from the formulas that that's what it is. You get an answer, but you still don't realize that that's just a centroid. And besides, yeah.
But it's the center of the triangle. How do you find the point?
Yeah, so that's true. So it's good and bad, because it's good because I never even use the fact that it's an ellipsoid. It could be any shape, right? And it's still a centroid. So that's probably. Oh, yeah, you're right. I don't know that it's where the point is, but if it's an ellipsoid, I can just do what's called a linear transformation. I can deform it linearly into by rescaling, so each coordinate by a different factor, I can turn it into a sphere, and then it's becoming a lateral triangle. Alternatively, I could say that the line through this point is bisects the opposites. It's a median. So that you can also calculate it from that. So basically, what happens, you cut out all the calculus. I mean, after that, you can use algebra. Yeah. Okay, but here's another, but this was a known thing, even though this result was published only in the 50s, so it's not such a known thing. Of course, with anything, there is nothing new. And the last thing, let me say, I asked this question, take any curve in contact, let's say, it's not an ellipse, it's just anything without indentations. The question is, what can you say about the triangle circumscribed around this thing of least perimeter? What can one say about the minimal perimeter triangle? That's the basic elementary question. And it turns out that the answer to that is, so of course, once you discover it, you can do it by other means, but I discovered it by physical property. It turns out that if you connect each tangent, special property of this best quote-unquote triangle, best means smallest perimeter, is the following: connect every tangency point with the opposite vertex. And it turns out that these all concur at one point. And moreover, the same is true for the perpendiculars. The perpendicular to this triangle, these perpendiculars also meet at one point. That's the concept. Another thing I can, so let me just say that I'm not going to do it. One time I was changing the bicycle tire and I asked myself, can you turn if you hold the bike wheel by the axle and it's not turning? The bearings are perfect. There is a bit from the gravity, right? So the bicycle wheel is perfectly balanced. Can you still turn the wheel without touching the rim or anything with perfect bearings? Right? And it turns out that you can by making the axle go through a cone. So there is again, physical proof of the Gauss-Bonnet formula, which is a general. Anyway, I'll just stop that if anybody wants to learn more. So, for me, I found it sometimes much easier to reprove the theorem than to read the proof. I mean, it didn't happen in many cases, but in quite a few cases in complex variables, I found it much easier to come up with a proof based on physical reasoning than to actually understand what's written in the book. So there is, I'm not saying this is a panacea, I mean, there's obviously this physical reasoning applies only to a subset of problems, but it can also be really. Yeah, I wish it was discussed in the textbooks, but almost never is. Okay.
Except in his book, I should like to advertise that there's a Princeton University Press book called The Mathematical Mechanic by Mark Levy. The Mathematical Mechanic, singular mechanic, as in mechanic with changes tires. And this makes an ideal Christmas present and the Thanksgiving gift and so forth. And it's not that expensive. The most entertaining book in mathematical science is out.
I also have a request because of the if you could address number 8 in particular, because I remember we talked about it earlier when we also put it on the poster about, and the email you sent me.
Okay, I can tell
If
you.
anyone caught it,
Uh,
or I don't know if anyone in the audience has caught it already. What's
Who knows what the polyhedral formula looks like? If you have a polyhedron, so it's basically a solid with spaces of polygons. Anything like that. So, there is a misprint in that. No. So basically you have two dimensions of vertices. V is the number of vertices. Number of edges, so the dimension 0-dimensional, one-dimensional objects, these are vertices, probably 0-dimensional, and 2-dimensional are faces. And if you do this, you will always get 2. It doesn't matter if it's a cube or a pyramid or anything else. It's 2, assuming this is a sphere-like, in other words, it doesn't have poles. And so the proof is based on the following. Here's one. Imagine that these are all wires. I don't care what the resistances are. And you take pump 1 amp into one vertex, doesn't matter which one, out the other. Of current. If you don't like current, you can think of tubes. But they're tubes with maybe some clogs, so the water goes through, but not completely free. And then if I say amp, I should say gallon per minute. Okay, that's it. Okay, and then here's the thing that I guess we have to take on.
So the wires are only the edges are the wires. The edges are the wires. So the faces are not.
That's right, faces are just hollow. It's just a frame.
So only the edges are wires.
Yes, yes. The rest is air.
So it's a circuit that consists of the vertices and edges.
Mm-hmm. So here's the key thing is that contains the whole idea. The rest is just the number of equations that determine there will be certain currents, right? So gallon per minute through each of these things, right? So the number of equations which determine the nature knows how to distribute the currents, right? It's 1 amp has to be split, and the nature decides how it's going to be split here and so on, right? And there is a heap of laws that determine how things get split, and that must be equal to the number of unknowns. Currents are the only unknowns. Resistances are given, I don't care what they are, but they're not because I've already built this machine, this thing. Okay, so let's count how many equations, and they should be independent equations. Well, what are the equations? For each vertex, the sum of currents coming into it is 0, right? Because whatever comes in leaves. If you want water, no water accumulates in the node. Net is 0. So that's the number of so for each, even here, right? Even here, the sum is -1. And here the sum is +1. So there we have as many equations as there are vertices. So V equations However, not all of them are independent, because if I know one of them can be determined from the others. Why is that so? So for each of these, let's single out one. I claim that this is zero automatically if I know that for each of these, the sum is either 0 or 1 or minus 1. How come? Well, if I say the sum of currents coming into here is 0 plus this, so if I add up all the currents that come into these vortices, right? For example, if I add this with this, whatever comes into this comes out of that. So this current will vanish, will cancel out when I do the addition, right? So every edge is going to count, every current is going to be counted twice when I compute how much comes into this and how much comes into this, but with the opposite sign, so that when I add up, these will cancel except for these guys. Right, and that's why these must also be 0. Okay, so it's really d minus 1. And the same, what else? The sum of voltage drops around each phase is 0. If you like plumbing better than electricity, then I can say the sum of pressure drops is 0. The pressure goes up, down, down, up must be, you come back to the same pressure as we had, so the sum of pressure differences is 0. And voltage is, voltage is the counterpart of pressure. So this is F, phases, number of phases, minus 1. But for the same reason, I'm not going to do it, but if you add the statement that the sum of drops is 0 over all of the phases, one of them is the, you single out this phase, and I claim that knowing that the sum for all other phases is 0 implies that over this phase is 0 as well, and it's exactly the same argument. In that case, it's because every edge is shared. When you go along the face in this direction, you count this edge with the plus, and when you go around this, you count this with the minus, and so on. Cancels. Okay, and that's how many currents we have? Well, we have edges. Each edge is unknown. That's it. So that's the formula.
So for something like if it were triangulating like a very force or something like that. With the
Very good.
factors
Yes,
form.
exactly. Great point. Yeah. So if you take a torus, so let me go. You see, it's a polyhedron which got a hole in it, right? What do we have? How do we have to fix this proof? Well, there is the number of equations is more, because you see, we need to say that the sum of voltage drops around this cycle is 0, so that's one more equation, and sum of voltage drops around this cycle is 0, so that's another equation. And so then you get the same formula with the 0. Every time you add a hole, you get 2. Because for every additional hole, you have 2 non-contractible cycles. Yeah. Yeah, so that's good. So the topology should be taught in conjunction with this. Yeah. It's funny sometimes, it's easier to know more than less. You don't know this side of things.
So yes, thank you very much, Professor. And we are very fortunate that Professor Levi is here for the rest of the quarter, but we are also very unfortunate that he's only here for the rest of the quarter as a visiting professor. So in the remaining 4 weeks, make sure to go pester him and 384Y and ask him more we didn't even get through all of the examples on here, but I've been told that Professor Levi has several more in his pocket that, if you know some complex analysis, if you know some sort of further theory of partial differential equations, of even more interesting slew of similar examples to look at. So if you're at all curious about those, please go find out at some time later in the quarter. We have refreshments set up outside. We'll bring out cookies soon. Professor, you're welcome to join us, and you're welcome to ask any more questions that you'd like right now as well. So thank you very much. All right.